Okay, we'll continue the reliability and security parts, and hopefully, again, I'm going to breeze through some of this, but we'll get to in-memory computation at the end of this. Remember, this is where we were. We were talking about reliability and security. We talked a lot about row hammer yesterday. Does this sound good? In the back? It's okay? Okay, good. And do you remember what it was? Hopefully. And we're going to talk a little bit more about row hammer. Remember, the row hammer is a phenomenon where you keep activating a word line. You keep hammering a word line, reading it, and that causes adjacent bits in the adjacent word lines, adjacent rows to flip. So why is this happening? There are actually a lot of interesting thoughts on why is this happening, and you should read the paper for more detail. But I gave you one intuitive reason of electromagnetic coupling. Because of the coupling between the two word lines, the word lines are too close to each other. Whenever you toggle one word line voltage, the other word line's voltage briefly increases, and as a result, you slightly open the adjacent row, and vulnerable cells leak slightly. And if you do it enough times before the cells get refreshed, you leak charge from cells that are vulnerable. That's one explanation, but it's really a combination of multiple effects, and it's really fascinating when the circuits become smaller. You get these really interesting noise phenomena that lead to errors. Conductor bridges are another of them. These conductor bridges get formed between circuit structures, so you get conduction paths that you don't normally expect because of the design of the circuit. And this is also really interesting, hot carrier injection. People have shown that if you hammer a row many times, what happens is you can permanently damage some other row because some hot carrier gets injected into an adjacent word line. Of course, this is very hard to show in real devices. People use circuit simulations to do that, but it's really a combination of these effects that we believe, and we've actually confirmed our hypotheses with at least one manufacturer who shall remain nameless, at least two actually by now, but all of these issues are getting worse actually as you scale the circuit down. So the row hammer phenomenon will stay with us for a while. Okay. So, remember we were testing DRAM chips, and I'm going to give you some results. This is where the row hammer phenomenon was discovered, by the way. These are the things that we've built so that we can test at scale. These are some of the results from the paper. Basically, most modules are at risk. I've already shown that. This is a scaling problem. I've already shown that. Errors are equal to charge loss. You can read the paper. I'll talk about this adjacency, aggressor and victim. So if you look at the row address difference between the aggressor is the hammered row, victim is the row that is victim essentially, that you're flipping bits on. If you look at the difference between the addresses of those rows, most of them are adjacent. You can see that the difference is either +1 or -1 as we expect, meaning that in the logical address space, these things are close to each other. But sometimes you get difference of 3, difference of 7, ... right? Now, what does this mean? This actually means that some of them are non-adjacent. Now, this could mean two things. One is the rows, the hammered row that's affecting the victim row is not physically adjacent. That could be one interpretation. Or these non-adjacent ones are actually physically adjacent, but they're mapped to somewhere else. Right? You're hammering this row, and you think that the addresses that are adjacent in the row address space are far away from each other, but in physical space they may be different because remember we talked about the row remapping internally in DRAM. DRAM manufacturers take one row. If there's an error in that row, a permanent error, they map it to some other row. So because they may do it in a systematic fashion, you may get these row address differences that are 3 or 7. So this may happen because of the internal address mapping, which we don't know in existing DRAM chips, but you can read some of the other papers that I have recommended later on. But I think the interesting thing is most of the hammered row and victim rows are adjacent to each other, which means that you can actually design mechanisms to solve this problem, at least for the most part. But that's not true for all the cases. Okay, let's talk about some solutions. So this is the access interval, how fast you access DRAM. Basically, what is the distance between two accesses to DRAM? If you actually change that, today you can access, this is the TRC delay basically, row cycling delay. Today you can activate a bank every 55 nanoseconds in different rows. That's allowed by the standard. Now, if we increase that access interval to the hammered row, we clearly reduce the number of errors because we're not accessing as fast. So in order to get rid of all of the errors, you need to increase your access interval to 500 nanoseconds, which is not good, right? You don't want to reduce your access rate to DRAM to get rid of all of these errors. Basically, if you're accessing DRAM less frequently, you get fewer errors. But if you want to solve the problem this way, it's probably not a good solution because you're actually increasing your access interval by a lot. Every 500 nanoseconds, you can actually activate a row. Not a good idea. Let's look at the refresh interval. These are all results from real DRAM chips. We're plotting just the worst case chips over here. What happens if you change the refresh interval? Today, we refresh everything every 64 milliseconds. If we do it more frequently, errors reduce. If we do it less frequently, errors increase. This is expected again because when you refresh, you replenish the charge in the cells before the cells charge actually data gets destroyed, right? But if you look over here, if you want to get rid of every single error that you see, you need to increase the refresh interval by 7x. That's a lot. Again, we want to get rid of refreshes, we want to increase refreshes, but there is a fundamental tension between errors and refresh in DRAM, actually. This sort of errors you can mitigate by increasing the refresh rate. You get rid of errors, but it comes at a cost, as you can see, right? Energy cost, performance cost, quality of service cost. So this is not a good solution, as we discussed yesterday, even though it solves the problem, because it's really increasing the refresh rate across the entire DRAM. Whereas this error is not a random error, if you will. It's really an error that's dependent on the access pattern. So if you're more intelligent about understanding what's going on, you can actually get rid of the errors in a much easier way. So that's actually really important. Going forward, we'll see a lot more errors. We cannot solve all of the error problems by increasing the refresh rate or by adding more error correcting codes. In fact, we have a lot of work that says if you add a lot more error correcting codes to Flash, you'll keep correcting errors, but if you're more intelligent about it, you'll correct a lot more errors a lot more efficiently. So you should really customize the protection mechanisms to the type of error that you're seeing. Okay, data pattern. This is also really interesting, actually. If you actually do row hammer, these are different rows, and these are the data patterns that are stored all once. If you do row hammer here, in these rows versus row hammer in rows that look like this, that are filled with this sort of data pattern, you get a lot more errors over here, like 10x. It's an order of magnitude almost. Why do you think this is the case? Coupling. Yes. Oh, okay. Yeah, that's good. Sorry. Exactly, yeah. Basically here, everything is, let's say, high voltage or low voltage, assuming one corresponds to high voltage or low voltage. The probability of leakage having a path between the two cells is much lower. Whereas here, one is high voltage and the other is low voltage. As a result, the coupling effect is much higher. The probability of leakage from one cell to another actually is very high. These are coupling effects. It's really capacitive coupling. And you can read the paper for more detail, certainly. Basically, errors are affected by data stored in other cells, clearly. So if you really want to launch a much more effective row hammer attack, you fill the memory with data patterns that look like this, if you can guess what those are actually. So actually, I think people are not doing this right now, but people can actually, if you really understand the underlying hardware structure, you can launch much more effective security attacks in the system. But that requires clearly understanding what's going on very much underneath. But I think that's happening, actually. After row hammer, there's a huge shift in the security community, in my opinion. They're really looking into how to attack hardware by exploiting the very, very low-level knowledge of what's happening underneath. I think Meltdown and Spectre actually was discovered by a lot of those groups that have actually worked on row hammer. So they actually developed the methodology to really figure out what's going on underneath. I think we're going to see a lot more hardware attacks that we may not expect going forward into the future. Okay, there are other results in the paper which are interesting also. I'm going to rush through them relatively quickly. I would recommend that you read this paper for sure. Victim cells are not the same as leaky cells. So if a cell that's vulnerable to row hammer is not the same as a cell that has a low retention time necessarily, because the phenomenon are different actually. Charge leakage is something different from what you discussed, electromagnetic coupling, hot carrier injection, and conductive bridges. Errors are not strongly affected by temperature. There is some effect, but it's not strong. I think there are more studies that need to be done here, but basically those things that we've discussed are not affected by temperature, whereas charge leakage is very much affected by temperature, actually. This also shows that there is not much overlap between victim cells and weak cells. Errors are also repeatable. This is actually the basis of a lot of the security attacks. Whenever you can induce row hammer induced error in a bit, you're going to be able to induce that again and again and again and again. It's a phenomenon related to the cell itself, which means that if you find out that a cell is vulnerable to row hammer, you can actually exploit it. Okay, so this is interesting. There are as many as 4 errors per cache line that we've seen, which means that if you use the existing error correction mechanisms that we have in error correcting DIMMs, like single error correcting, double error detecting error correction mechanisms, you cannot prevent all errors because you get 4 errors, as many as 4 errors. You can prevent most of the errors, but you will still have some errors. And I think going forward, the problem will become much worse. So adding more ECC is not a good use of your error correction capability for this type of errors. There are a bunch of other interesting results. For example, you can actually have many victim cells. Whenever you bang on a row, hammer a row, you can actually affect as many as 110 cells. That's a lot. And you can have many victim rows also. It's not just the adjacent row. You see the effects in a little bit farther rows also, which is interesting. And we've also discovered this, and Google later exploited this, as I said. Cells are affected by 2 aggressors on either side, so you can actually do double-sided row hammering, as the good folks on Google, at Google have discovered. By the way, you can download all of the source code from our GitHub and try row hammer on your machine, or you can download Google's code. Google's code is better, I think, because they built on our code and improved it, and try row hammer on your machine. It should be fun. See if it's vulnerable. A lot of people have done that. You can actually see online people are saying, oh, I don't see it. And other people are saying, oh, you should do it. You should do this, this, this so that you can see it. Okay, and this is the paper. You can take a look at it. And I'm going to talk a little bit about this paper in the next. But I think basically we have a huge challenge and opportunity for the future, and it's really building secure, reliable, and safe computing architectures. And this row hammer phenomenon is one example. Now let's talk about some other examples in memory, especially in the intersection of reliability and security. Of course, security is a huge area. We're not tackling the huge security part. As I said, security attacks are shifting very much into hardware today. We're going to see a lot more hardware attacks. So this is the future of main memory. Basically, what I've said is DRAM is becoming less reliable, which means that it's becoming more vulnerable. And I've already given you this paper, and this paper showed that as chip density increases, you get a lot more errors, which causes server failures. And how we actually, one interesting thing that we found when we did these studies on Facebook servers is existing systems are not actually very good at handling some of those errors also. Even though error correction codes can detect them, sometimes what happens is you get these interrupts because the hardware memory controller detects the errors, but it detects so many errors that it overwhelms the operating system, and the operating system isn't able to handle all of those interrupts, and as a result the system crashes, or you get a system hang. So we need to have actual system level mechanisms for handling the errors in good ways as well. So some of the results that in the paper, this paper shows explains that. The other thing that we show in this paper is they're really interesting things. So sometimes what happens is in the data center, a DIMM, a memory module gets unseated a little bit, and as a result you start getting a lot of errors, channel errors, and that's when the system becomes overwhelmed. So if an engineer or an operator goes and reseats the DIMM, make sure that connections are good, you get rid of the errors. So not all errors are really cell errors. Some of the errors are because of how stable the system is. Like our projector over here, because our projector, I believe, is not stable. Today we're getting flickering on our machine over there in the camera. So a lot of these there's a lot of analysis of the errors here. So how do you actually correct these errors? One of the operating system level techniques, whenever you discover an error, is offlining a page. So if you discover a lot of errors on a page, you say, I'm going to offline this page. I'm not going to allocate data over there. This is a very easy technique that are used by operating systems, and Facebook employs it. And we actually analyze it at scale in this paper. So if you're interested in solution mechanisms and the reasons why some of these errors are happening, this paper has a lot of data in it. And we've done similar studies for flash memory, again with Facebook, but they were very open about actually having us analyze the errors. Maybe they didn't let us report everything, but we were able to gather insight into a lot of flash memory errors, which I'm not going to really talk about. But if you're really interested, errors are in the end, memory errors are in the end very similar across different devices, but flash memory also has a lot of errors. So one of the findings over here is we found that there are many findings, but one of them is we actually see a lot higher error rate in the field than what we expect from the flash devices, especially at the end of their lifetimes, like 3 years or 5 years. Maybe that's not the end of the lifetime, but sometime after they're used for a while. Okay, so we've said this already. Basically, due to difficulties in DRAM scaling, I think other problems may actually appear, or they may already be going unnoticed. This is really interesting. Some of the errors we are seeing may be potentially due to row hammer. Actually, other people have said, anecdotally again, they've analyzed some of the supercomputer errors in large-scale supercomputers in the US, and they said they have evidence of this sort of read-disturb errors happening in memory. Retention errors could be happening. This is very hard to really say. It's very hard to pinpoint the root cause of some of these errors if you see an error in the field. You know that you see an error, but what's the root cause of it? It's very difficult to say exactly. Read errors, write errors, and there are some random errors, of course, soft errors. Soft error probability, the probability that your bit kind of flips because of whatever reason, maybe a particle strike, is much lower than some of these error rates. Okay, so these errors can also pose security vulnerabilities. The question is, can you actually take advantage of it? Yes?
Every time you read DRAM, for example, then you also write back. So what will be the difference with read attacks and write attacks?
That's right. So readers, that's true. Every time you read, you actually form a feedback path. So write errors may happen in the write circuitry of DRAM. Basically, if your write drivers are failing for whatever reason, that's not exercised when you're actually reading. Okay? Or on the bus, for example, if you're driving the bus with some data value and your channel is not stable for whatever reason, you get those write errors. So that's the difference. That's a good point, though. Okay, basically, let's talk about retention time failures a little bit. We talked about refresh a lot, but I think now we're getting to the core of the scaling problems in DRAM. Determining the data retention time of a cell or row is getting more difficult. And if you say, I don't care about this, you should really care about security. Because if someone figures out how to exploit this predictably, then we'll be in trouble, I think, going forward. And actually other people have said, oh, this is the DRAM manufacturer's problem. Why should we care about it? And I'll tell you why it's not just the DRAM manufacturer's problem. It's really the system's problem. And if it's a system's problem, it's our problem. Okay, so retention failures may already be slipping into the field, and as I said, we've done a lot of studies. This is our first study, actually. This is the first study that we published after we built that infrastructure. And that infrastructure took about 1.5 years to build to reliably test DRAM. And I'll talk about two challenges to retention time profiling. These are really fundamental challenges. And one is data pattern dependence or retention time, very similar to what I showed with row hammer. Row hammer is very much data pattern dependent. And the second is what we've discussed earlier, variable retention time. So what does this mean? Data pattern dependence, DPD. The retention time of a DRAM cell depends on its value and the values of cells that are nearby it. Why does this happen? When you activate a row, all bit lines are perturbed simultaneously. These are the bit lines. These are the word lines. When you activate one row, you really perturb all of the bit lines that are connected to that word line. These are the bit lines. And what happens is there's electrical noise on these bit lines, and that electrical noise affects the sensing of a DRAM cell that you're trying to read in the DRAM cells that you're trying to read in the rows. And the magnitude of that noise is affected by the values of the nearby cells. So assume that we're looking at this cell. The magnitude of the noise that you get on the bit lines is affected by the nearby cells, these two, for example, or maybe these two also. Because of the bit line to bit line coupling, there's electrical coupling that happens between these two adjacent bit lines over here. This bit line is affected by these two bit lines, for example, and maybe even farther away bit lines, less so. Or bit line to word line coupling. The value that you see on this bit line is affected by what's happening on this word line. So if you have noise on this word line, the value that you read over here is dependent on basically where does that noise come from? Noise comes from what value you have over here also. So that's the fundamental reason of the data pattern dependence, which means that the retention time of a cell, how fast the charge leaks from the cell, is dependent on what's happening in other cells, what's stored in the other cells because of this coupling effects. So you need to find the worst data pattern to find the worst case retention time. Remember, the key question is, what is the worst case retention time of the cell? How often should I refresh the cell so that I'm reliable? And you need to find the worst data pattern. Now, how do you find that? This pattern is actually location dependent also, because there is a lot of process variation, and there's also circuit organization that affects what is the worst case data pattern. So this is not an easy thing to find, actually. The worst case data pattern for one row may not be the worst case data pattern for some other row. DRAM manufacturer can help a little bit, but they also, because they know at least the circuit organization, and they can say, oh, maybe the 11001 is the pattern that is worst case, but they don't fully know all of the manufacturing variation, right? Process variation that happens due to manufacturing. Okay, this is hard. But there's something even harder, as we've discussed earlier, which is the variable retention time phenomenon. Basically, the retention time of a DRAM cell changes randomly over time. I've described this earlier, but I'll describe it pictorially. A cell alternates between multiple retention time states. The reason it happens is because you have charge leaks from this capacitor, and the leakage current over here, it changes sporadically, because charge gets trapped in this access transistor sometimes. As I said earlier, when this trap over here becomes occupied, charge leaks much faster from the capacitor through the access transistor's drain, and it leads to short retention time. And as I said earlier, this is called trap-assisted gate-induced drain leakage. And it appears to be a random process. Other people examined it. It was first discovered in 1987, as old as 1987. But it's becoming much worse, as I'll show you. So worst case retention time depends on a random process. Now, if you want to answer the question, how often should I refresh DRAM? The answer is random. Not good, right? Because you don't know, basically, because of this. So how do you actually deal with this? Okay. Basically, this what this also says is DRAM manufacturer can keep testing memory, but if they don't hit those conditions under this trap-assisted gate-induced drain leakage appears, then they're not going to be able to find the worst-case retention time. Right? So you can say DRAM manufacturer should solve it, but the DRAM manufacturer may not be able to solve it because of the fundamental difficulties in scaling of the circuit. So somebody else needs to solve it. Also, there's another effect that's not captured here. So you can test the DRAM. Let's assume that you find the ideal retention time after you manufacture the chip. You take the chip, you solder it on a DIMM. While you're soldering, you expose it to very high temperatures, let's say 300 degrees Celsius, depending on your process, of course. Now, once you do that, it turns out that affects the retention time of the cells. Now, you cannot blame the DRAM manufacturer for that, right? Meaning that because you're changing the retention times because you want to put this chip in a form factor that you want to be able to use. So somebody else needs to figure out the retention times. And I think we're going to talk about what could be the potential solutions. But let me show you some results over here. These results are obtained at 45 or 50 degrees Celsius. That's why the retention times are very long. This is from the paper that I described. This is the retention time that we've tested and the fraction of cells with retention time less than the x-axis value. So this is a curve that we would expect. Most of the cells can retain data a lot. But newer device families have more weak cells or leaky cells than older ones. This is likely a result of technology scaling. For example, this is an older technology. The curve looks like this. This is the same manufacturer with a newer technology. The curve shifts to the left, meaning that your retention times are reducing overall. That's true for all manufacturers again. Older technology, newer technology, the curve shifts to the left. You have more cells that have smaller retention times. This is the phenomenon. Again, this is real data from one of the other manufacturers. We had tested 5 manufacturers over here because, believe it or not, there are some small DRAM manufacturers that exist. And this is an example of variable retention time cell. This is, you test, let's say, over the course of 10 hours in this case, and you look at what's the retention time of the cell. You see this sort of behavior. The retention time basically jumps up and down between 2 or 3 states. In this case, the retention time is about 2.5 seconds. In this case, the retention time is actually much longer than what our longest testing interval is. Basically, sometimes you get very low retention time, sometimes you get very high retention times. And you see this is seconds. It's not 64 milliseconds, again, because of the temperature. Temperature is much lower in the tests that we do because we don't want to damage the chips by operating them on very high temperatures also. So this is another example of the variable retention time phenomenon plotted in a different way. This is, we plot all cells over here. This is the minimum retention time that we see for a given cell. And this is the maximum retention time that we see for a given cell. And the maximum retention time we test is about 6 seconds over here. So ideally, if there is no variable retention time phenomenon, what would you expect? You would expect x equals y curve, right? All of the cells fall on this line, because minimum and maximum should not differ. But what we see is almost exactly the opposite. Most of the cells are actually over here. Most failing cells actually exhibit a variable retention time. And actually many of them are over here. Many failing cells jump from very high retention time to very low. Their minimum retention time is very low over here. Their maximum retention time is very high. So there's a huge range in terms of retention time. And these are very real scaling issues that you have with circuits. Okay, if you want to see more data, this is an example data. This is true for many chip families, all manufacturers basically, and there's a lot more data in this paper. So as I said, industry is writing papers about it too, and without providing data, but they say that the phenomenon exists and we need to be intelligent about solving the problem. By the way, variable retention time is interesting because it's a random error. Error correcting codes are a good idea to solve that kind of problem, right? It's a random error. Whenever you have a random error, if you're having an error correcting code, fixing that error that's applied uniformly across your entire device is helpful. And that's exactly the reason this paper also proposed, we're having difficulties, so we should put error correcting codes inside our DRAM chips. And that's exactly what's happening in existing DRAM chips. As I said in a couple of lectures ago, I think, if you buy a cell phone next year, you'll definitely have error correcting code DRAM inside it. Okay. So let's talk about refresh a little bit. Why is this interesting? It's interesting from a security perspective, but we don't have attacks related to this yet. I believe some people will develop as the understanding grows. But refresh is also interesting in itself, and this is an example of how refresh is limiting the scaling of DRAM. This is based on the paper that I recommended in the past. This is device capacity on the x-axis, and the percentage of time the device is expected to keep refreshing itself. Or the throughput loss of the device. You cannot access the device while it's refreshing. So today, it's relatively low, maybe 10-12%, but it's expected to grow as you increase the size of the chip. Why? Because when you increase the size of the chip, you're adding more rows, which means that you need to refresh more rows. And also, you need to go to lower technology nodes, and as a result, your retention times will reduce. Things will become more leaky. And this is the energy impact. Basically today, of course, this relies on a lot of assumptions on what fraction of accesses you have to DRAM, and this is not the idle energy. Also, idle energy actually dominated by refresh and leakage, but this is assuming some activity factor. Today, it's about 15%, let's say, but going forward, it'll go up to about 40-50%. So does it make sense to manufacture a device where which you cannot access half of the time, and which is wasting half of its energy just on refresh? Actually, one of the assignments that I give to my students in even my freshman courses, they should calculate the amount of kilowatts or megawatts that are spent on refresh if you have a huge supercomputer that consists of exabytes of memory, assuming the current and assuming the future expected trend for refresh. And it turns out to be on the order of, well, if you start with a small memory, it starts with kilowatts, but you easily get up to megawatts quickly if you have huge amounts of memory. And existing supercomputers are already getting closer to, I think there are more than petabytes of memory for sure, but they're going to be exabytes of memory relatively soon. And as we said, you can actually take advantage of the retention time profile of DRAM. I'll go through this relatively quickly because we discussed it. Basically, the observation is that most DRAM rows can actually be refreshed much less often without losing data. This is actually data from Samsung. They published a paper a long time ago. And the key idea, if you know this information, one key idea could be you refresh the rows containing weak cells more frequently, all other rows less frequently. For this, you need to profile the retention time of all rows. You need to know that information very well, the minimum retention time. But as I said, we're having difficulties. We're going to talk about that. Assuming you know that information, what can you do? You can store the rows into bins by retention time in the memory controller. The memory controller stores this information, and you can do this relatively easily using Bloom filters. How many people know about Bloom filters here? Okay, not enough. Anyway, I don't have time to cover Bloom filters, but you should definitely watch my undergraduate freshman lecture at ETH that talks about Bloom filters. I think it's lecture 2 or 3. This is something that could be useful for the rest of your life. Bloom filter is essentially an approximate representation of a set. It's a bit vector that approximately represents whether some elements exist in the set or not exist in the set. In this case, it makes sense because once you figure out rows, let's say you want to figure out which rows need to be refreshed frequently versus not frequently, it's really representing the set membership of those rows, right? You take the address of the row, hash it, and store the associated bits, set the associated bits to 1 in the bit vector in the Bloom filter if it needs to be refreshed frequently. And later, you store that information in the memory controller, and the memory controller, when it needs to refresh a row, it checks whether it should be refreshed frequently by looking up that Bloom filter. And if it gets a 1, it says, oh, I'm going to refresh it frequently. So it's a very fast, approximate data structure. It was invented by Burton Bloom, I think, in 1970. It's Communications of the ACM 1970. And actually, there are many, many hardware and software algorithms that make use of it because it's very compact. As you can see, for 32 gigabytes memory, you can store this retention time information for only 1.25 kilobytes. And even that can be reduced. Okay, and the memory controller refreshes rows in different bins at different rates by checking these Bloom filters very, very quickly. So this is a very practical mechanism. So what does it buy you? We simulate, because you cannot implement in a real system. Basically, it reduces refresh by about 75%, as expected, because of the retention time distribution, as I showed you earlier, at very low storage cost. And it leads to about 16% DRAM dynamic power reduction, 20% reduction in the idle power. And it also leads to performance improvement, about 9%. So it's actually good for almost everything, right? Performance, quality of service we didn't test over here, but it also improves quality of service. And it's also, the benefits of this increase with DRAM capacity. For example, the energy per access reduction, if you had a 64 gigabit chip, is 50% as opposed to 16%. Because retention time refresh becomes a much bigger problem at much larger chips that are manufactured at smaller technology nodes. So this sort of ideas are really important, I think, going forward. We need this sort of ideas to actually scale the systems into the future. But if you look at this curve, ideally when you increase the size of the chip, you would like the energy per access to be constant. Well, ideally you would like it lower, of course, but maybe that's too ideal. Ideally you would like that energy per access to be constant. This is the green part over here with Raider. It turns out even Raider is not enough if you have a chip that's very large. So you really need more techniques to develop to solve the refresh problem. So if you know the retention time distribution, of course, you can do other things. You can expose this information to the operating system. The operating system can say, oh, these weak rows, now I know of them, I'm not going to allocate stuff on them. Right? That's another solution. Maybe that's a simpler solution, but that requires even more interfaces to be exposed to the operating system. So all of these actually require interfaces between the memory controller and the operating system, and maybe the DRAM chip as well. And those interfaces unfortunately, are very rigid today. We're going to talk about that when we talk about in-memory computation also. Okay, so the key issue over here is how do you figure out the retention time of all rows? So this was the first paper that we wrote on refresh. It was a really good idea. I still believe this is a really good idea. How do you actually implement it is the key question. And it's really bottlenecked by whether you can figure out the profile retention time of all rows. As I said, it's not easy. There are issues. That's why we actually ask this question next. How can you reliably find the retention time of all DRAM cells so that we can enable, either make DRAM reliable and secure and make techniques like Raider work so that we can scale the technology into the future. And then we wrote a bunch of papers. I'm going to go through some of them. And this idea, I think, is very interesting. Basically, in this paper, we examined several things. Wow, this is very quick. Basically, you can keep testing DRAM, but you cannot detect all possible failures. I'm going to show you data later on. So you can have an online testing system that keeps testing DRAM while the DRAM is being in operation. It's not happening right now, but it could happen. But you cannot detect all possible failures. So basically, you need some error correcting codes to deal with variable retention time issues because you don't know the retention time perfectly. So you need to combine them with other mitigation techniques like online profiling, but then you degrade performance, and how do you control performance? And also there's another thing, testing can help reduce ECC strength. So there's a trade-off between different approaches to solving the retention time problem. You could keep testing, figuring out the retention time and adjusting the refresh rate of a row based on what you figured it out. But it's more effective if you have ECC. And if you have a strong ECC, you can actually reduce the strength of the ECC. Let me give you a pictorial example. Basically, if you want to figure out the retention time of rows online while the system is in operation, which is what we really need to do because we cannot figure it out offline, you start with some error correcting codes that are protecting memory. Let's assume you initially protect DRAM with strong error correcting codes, and then you have a refresh rate, and you periodically test parts of DRAM and figure out, oh, some of them can be refreshed less often. If you refresh it less often, you basically can reduce the error correcting codes that are dedicated for some parts of DRAM. That's the idea. Because you don't need that much error correction because you have figured out online that, that these rows are strong. I'll give you another example. This is data pattern dependent, right? If you know the data pattern in DRAM, for example, if all rows are, all of the cells are discharged and all of the cells around them are discharged, maybe you don't need to refresh DRAM at all, right? In that case, if you know the data. Even though you need that data, you don't need to refresh it because you know that charge is not going to leak from there. So that's very powerful if you can exploit that, the knowledge of what the content over here is. Then you don't need error correcting codes as well, right? Okay. So basically, you can actually do this. You can run tests periodically after a short interval at smaller regions of memory. And if you're interested, you can read the previous paper. Let me give you the idea of this paper, because I think this is the state-of-the-art solution to variable retention time. It requires error correcting codes. So variable retention time, I think the takeaway here is, because it's a random process, you don't know the retention time, you have to have error correcting codes. And that's exactly why the industry is moving to that, but you can be more intelligent than what the industry is doing. So this is what we proposed. Basically, we wanted to avoid retention failures, and you can have a refresh rate table for each row. This is pictorial. Basically, you protect each row with error correcting codes, and you basically have a refresh rate table that says whether this is a weak row or a strong row. Weak row means you need to refresh it more often. Strong row means you need to refresh it less often. And once in a while, basically you get errors. For example, this is a weak row. Initially you identify it as a weak row, but you have enough ECC. Because you don't refresh it, you get an error, but the error correction code corrects that error. If you figure that out, what you do is you essentially upgrade that row. Say, oh, now you need to refresh this row more often. That's the idea. So basically, based on the feedback that you get, you refresh it less, you get an error, error correcting code corrects it, and it tells you, oh, you should refresh it more often next time. That's the idea. And you can upgrade it with 1 bit over here. So row is protected now from future retention failures, hopefully. And that's the idea of Avatar. And you do this also when you're scrubbing the memory. Scrub is employed in especially server systems today. Every 15 minutes or so, for example, every hour, the server memory tests itself, or every day. And it basically corrects the error correction codes. If it reads and writes into memory, and it basically corrects the errors. And you can actually figure out whether you get errors at low refresh intervals, and based on that, you can actually upgrade the refresh interval of the cells accordingly. I'm going through this relatively fast, but it's a very simple idea. If you get an error, increase the refresh interval. There's this really interesting continuum in terms of retention time. You can solve the problem by refreshing extremely frequently, or you can solve the problem by having very strong ECC. Both of them are not good because they have both overheads. You really want to be somewhere in between, and you want to employ the intelligent solution. Right? You don't want very strong ECC. You don't want extremely high refresh rate. How do you actually achieve somewhere in between that gets you a much better performance and energy trade-off and good reliability? And that's the idea in this paper. And what are the benefits? Basically, assuming that you have no variable retention time. So remember, Radar assumed that you know the retention times. But later we tested and we figured out, oh, retention times you cannot know beforehand. So you really need to online update your retention times. So this is the ideal case, assuming basically some refresh rates, of course. You get rid of about 75% of the refreshes in this case, maybe 72, depending on the assumptions you have over here. But Avatar adapts to what happens online. Basically, online it figures out variable retention time errors keep happening over the lifetime of DRAM, and it figures out, oh, these are happening, so I'm going to adjust the refresh rate for them. So over time, the refresh rate savings degrades, but it's not that bad. Basically, you still get rid of 60% of the refreshes, but now you're reliable. Right? If you think about it, radar assumes that you have a static profile and it's not reliable. Okay, and you can also do retention testing once a year, and maybe you can move that curve up, but you can read the paper for that. So what are the benefits of this? This is actually the performance benefits. In a 64 gigabit chip, you get about 35% performance improvement with Avatar over the course of a year, after a year. And the no refresh case is still higher performance improvement. So there's still a gap, basically. There's still things you can do to improve performance. And this is the energy delay product that you get with Avatar. Again, over a year, this is what you get. But you can read the paper. Basically, you reduce energy delay product, and especially at higher capacity nodes, you get much better trade-offs. Okay, I'm not going to go through some of the papers that I'm going to rush through over here, but we have there are interesting solutions for data-dependent failures. And all of these papers are actually driven by real data from DRAM chips. I think that's really necessary for doing this kind of research. You have to have real data, and I'm going to emphasize the importance of it later on. And you can actually exploit the current memory content to reduce the DRAM-dependent failures, as I mentioned earlier. Yes?
What is the relation with this, what you just showed us, with the walking beat test and all those memory tests?
Well, all of those memory tests, so actually what we're doing is we're doing some memory tests online while the system is operating. The memory tests are traditionally done before you actually ship the chips. So basically we're doing some of the tests online, but you need to be very intelligent about what tests you employ online because it has very severe implications on performance. So basically the vision is that DRAM manufacturer doesn't identify all of the retention time because they're not able to. The system online identifies all the retention times and optimizes its behavior. And you need an intelligent memory controller to do that optimizes for the tests. Okay, I'll very quickly talk about this. This is actually one of the most recent papers that we've done in 2017. Yes?
Do you have done an analysis of the energy consumed of online profiling?
So this paper has that analysis. I'm not going to talk about it, but take a look at this paper. Energy as well as performance. So this paper actually looks at the most modern DRAM chips, LPDDR4 chips in mobile phones that are used in mobile phones and also mobile laptops, and to analyze the complex trade-off space between retention time profiling. And the idea is to enable fast and robust profiling, online profiling, at higher refresh by doing it at higher refresh intervals and temperatures. I'm going to go through this relatively quickly because we don't have a lot of time. But if you're really interested, this is really the state of the art. And you know the problem by now. You have leaky cells, you need to periodically refresh DRAM, and this leads to performance and energy overhead. And the goal we have is to find all retention failures for a refresh interval T that's greater than the default. Right? So how do you do that? There are a bunch of effects, as we've discussed, that are not good. And so we characterized a large number of LPDDR4 chips. This is really the state of the art. And cells are more likely to fail at a higher refresh interval and temperature. Which means that you can use this actually to profile. If you want to figure out whether a cell fails at, let's say, 64 milliseconds, you profile at 128 milliseconds, or maybe 4x the retention time. Basically, you increase the refresh interval, and you find the cells that are failing, and you say, oh, this cell is likely to fail at a lower refresh interval as well, or higher refresh interval. I'm going to give you an example. Basically, this is your refresh interval. This is your temperature. Ideally, you would like to operate here. But if you really want to find all of the failures, you want to profile at aggravated conditions, at higher temperature and a higher refresh interval. So that's the key idea in the paper. But there's a lot more analysis. And let me actually give you some of that analysis over here, because it's really interesting. Things are getting much worse. That's why you need to understand the different devices, and that's what we did over here. And this is not new. So let me give you an example of the testing that we've done. Basically, this is about a week of testing of a particular representative chip from some vendor at some retention time, at some temperature, and the temperature is constant. Basically, this is the variable retention time phenomenon you see. You always see new failing cells. As you keep testing, you keep cells that are failing, and you keep accumulating. These are unique cells, actually. So sometimes you can see that this is one cell at the bottom over here. You mostly see one cell failing, but you sometimes see a lot higher, 2 cells, sometimes 3 cells. So you get these errors as you operate DRAM, and it's just days, right? 7 days. Imagine a year. This is the state-of-the-art technology. Well, it's not state-of-the-art anymore. This is 2x nanometers. So basically, the key conclusion is you have to have error correcting codes and online profiling to manage the new failing cells. So let's take a look at, I'm going to be a little bit deeper here, but this is the refresh interval. This is the probability of a read failure of a cell. Ideally, you would expect something like this, right? But you don't see that actually. The errors are much more probabilistic. The errors look more like this. The actual cell has a probability distribution of errors, and it looks like kind of like this. And these are some real cells. This is real data, for example. We examined the lifetime of a cell, and we tested many times, and this is the failure probability. Out of 16 trials, this fails about 9 times. This is zooming into a particular time interval, of course. And there are different cells that fail at different rates, as you can see. So cells are not equal also, which means that you have a difficult problem. Of course, now you fit the distributions. This is a fitted distribution, as you can see. If you want to operate at a refresh interval at 1.7 seconds, let's say, we just made it up over here, you want to find the failing cells. So clearly these cells are failing, right, at 1.7 seconds refresh interval, because they're failing with at least about 10% probability. So if you test, these are hard to find, basically. Especially these are hard to find because they don't fail very often, right? This fails 100% of the time, so they're probably easy to find. So if you're actually intelligent, you increase the refresh interval a little bit and do the profiling over here. And once you do that profiling, what happens is now you can more easily find these cells that would fail at a lower refresh interval over here, which means that you can actually have much coverage. But you also find some cells, okay, that fail at this higher refresh interval over here, which means that you're going to refresh them more frequently. These are called false positives. So that's the downside of profiling at a higher refresh interval. If you really want to understand it, you should really read the paper. But there's a lot of interesting data. And I think to be really able to understand what's happening in scale technologies, you need to build this sort of models. And this is a cell level model, as you can see. Okay, basically any cell is more likely to fail at a longer refresh interval or at a higher temperature. So that's the idea of reach profiling that I gave you over here. Because you know this, profile at a longer refresh interval and or higher temperature. It turns out this is faster and reliable. It searches for cells where they're most likely to fail, but it causes false positives because the profile may identify cells that fail under profiling conditions, but not under operating conditions. But maybe it's okay. False positives are okay because you refresh the cell more frequently than needed, but that's okay perhaps, right? So the paper answers a bunch of questions. It's really a general methodology of profiling. What are desirable profiling conditions? How often should the system profile, and what information does the profile need? I'm not going to talk about that. And there are a bunch of metrics, as you can see. How long the profiling takes, what is the energy and performance cost, what is the coverage, what fraction of the cells can you really identify, and false positives. Well, let me give you some results. Basically, there's a lot of results over here, but I'll go to the conclusion. Essentially, if you do this sort of real profiling, this is a real profiling-based end-to-end system, you can improve system performance, according to our results, by about 16% and reduce DRAM power by about 36%, according to our data from the most recent devices. And it turns out this enables longer refresh intervals, which are unreasonable using brute force profiling. What do I mean by brute force profiling? This is the unreasonable testing. You don't profile intelligently, but basically you profile once in a while all of the cells in DRAM. So that's not good for system performance, it turns out. Okay, so if you're really interested, you can take a look at that paper in more detail. I talked about this because this is the most state-of-the-art work. I talk about the earliest work and some in-between works and the most state-of-the-art work. So if you're interested, there's a lot here. And I think this is true for other types of failures. People need to do this sort of analysis for other types of failures that we're seeing in systems. I hope that happens going forward. And we're going to talk about this later on when we talk about latency. So basically, how do we keep memory secure? I'm going to try to conclude this part of the lecture at least. We want to have principled designs, in my opinion. Well, let me go back. This is true for any type of memory. DRAM, we've focused on a lot. Flash memory, I have some backup slides. I don't think we're going to be able to cover flash memory. Emerging technologies, they all have different sort of error problems. These are non-volatile, for example. You can say, oh, I don't need to refresh phase change memory. Think again. Actually, these are resistive memories, and resistance shifts over time. As a result, you actually need to refresh. Flash, very similar. It loses charge as the flash cells wears out. You need to refresh. And as flash becomes closer to the end of its lifetime, you need to refresh it very frequently. Maybe not every 64 milliseconds. According to our results, you need to refresh it maybe every 3 hours or so. But if your flash is not actually connected to a power source, how do you even refresh it? It's supposed to be non-volatile, right? So think about storing critical data on your USBs, which really don't have even intelligent controllers in them, right? We were discussing this sometime. Okay, but all memory technologies will have this sort of problems. That's why I'm harping on it. And we're going to see more and more of this. And they lead to security issues. So we need to somehow design fundamentally secure architectures. I believe that requires predicting and preventing these issues. So how do we do that? This is my proposed methodology. We need to understand, first of all, we need to have really solid experimental methodologies for modeling failures and discovering failures, predicting failures. So how do you do that? I don't think there is any easy way to do that without working on real devices. You need to perform these models by understanding the real device behavior, both at small scale as well as large scale. And I've given you examples of small scale and large scale. And you need to develop metrics for security based on this. I think retention time is one example, but I think we're very far away from developing real metrics for secure designs, right? I mean, side channels is an example that we didn't talk about, but even that's even harder perhaps, right? Okay, so how secure is your system if you have this sort of error behavior that's happening in DRAM and all other parts of the system? This is something to think about. And after you do that, maybe you need to have principled co-architecting of system and memory. How do you actually solve the problem, or how do you actually have a solution that can be employed when you discover these errors in the field? I think that requires certainly good partitioning of duties across the stack and patchability in the field. A programmable memory controller helps, for example. If you can, for example, execute instructions to the memory controller such that you can patch your memory controller to fix some of these issues, that at some performance cost, maybe it's okay, right? And I think designing and testing is really important. We really need to design for security. We're designing for performance and maybe energy a little bit, maybe reliability, but we're really not thinking about security in hardware design. But we really need to be thinking about it going forward. And of course, I think security is very much affected by not only design, but also testing. You keep testing and you figure out security vulnerabilities over time potentially. And that requires good interaction with the reliability methods that we employ in the system as well. Anyway, there's a lot here. We can think about it, and there's a lot to think about. So I think that's what we've been doing. We want to understand and model with experiments DRAM. We've been doing it for flash also. And I'm not going to go over the flash because we just don't have time for it. But I'm going to refer you to this paper for flash, and this paper as well. But flash is interesting because I'll spend very little time over here. It turns out read disturb issue exists in flash, and we found that this could also be a security vulnerability. I believe it's a security vulnerability, but it's very hard to exploit because flash memory sits very far away from the processor. In order to be able to impact a bit over there, you need to go layers and layers of the software stack, layers and layers of the firmware stack, which includes the flash translation layer. And if you want to induce errors predictably at some locations, even when you know the device behavior is very unreliable and you get predictable errors over there, it is not that easy. Whereas DRAM, if you think about it, well, for flash you need to go through the file system interfaces, right? For DRAM, it's directly exposed to your programming language. You write to an array, or you read from an array, that directly appears on your memory. That's why security issues are a lot easier to exploit if it's directly in your main memory. Right? I think flash has very similar issues, but they're very hard to exploit. But I believe really smart people, if they put their mind to it, they can exploit the security vulnerabilities that exist in flash memory also, especially with emerging memory technologies when flash memory becomes much faster and people try to get rid of all of that software stack as well as the hardware stack so that they can take advantage of the speed, bandwidth, and the latency advantage of that technology. Once you get rid of that stack to access non-volatile memory, it looks very much like DRAM, right? And now you really want to access that through your programming language. You don't want to really have the file system to limit the access rate that you have to your non-volatile memory. But now you're also exposed to security vulnerabilities like we've discussed with rowhammer. Right? And I think rowhammer is a very fundamental phenomenon in other memories also. Okay, so if you're interested, this is one example with existing flash technology over here. And we've been looking at more 3D NAND flash reliability. This is really fascinating. I'll take some time over here about this. Unfortunately, we'll have to start in-memory computation a little bit later, because this is really fascinating to me. But one thing that happened in flash memory is, this is where technology can really help you. Flash memory was not scaling very well. The error rates were increasing very high when you had planar flash. Planar means two-dimensional. And manufacturers were able to, essentially, they had a breakthrough, and they were able to stack flash cells vertically. And because they were able to do that vertical stacking, which is called the 3D NAND device, or Samsung calls it VNAND. Samsung was the first manufacturer to be able to do this reliably. What they did was they were able to gain more capacity by vertically stacking, and they didn't need as small transistors anymore to get the same capacity. So they increased the size of the flash transistors, but they stacked more layers. As a result, they got higher capacity, higher reliability at the same time. So that's beautiful. But there are some other issues also over here. But it turns out if you can find a technology like this that can get you higher capacity and higher reliability at the same time, you should always take it and invest in it. And that's what happened in 3D NAND technology. But again, technology is very fundamental. What they're going to do is they're going to increase the size. They want to increase the capacity. How can they increase capacity? They're going to stack more layers vertically. That's going to add more interference. And at some point, vertical stacking will be impractical. What are they going to do? They're going to reduce the size of the flash cell. Today, planar flash cell is about 10 nanometers or 15 nanometers. What they were able to do by vertical stacking is they were able to increase the flash cell size to 40 nanometers. That's amazing. You don't scale down. You actually scale up the size of the cell. But they're going to scale down, and they're going to see the same error issues going forward. The technology gives you a bump, gives you more time, but eventually you will hit the scaling limits, unless you move to some other technology again. So I think that's really the interesting thing that we've been seeing in computing. You don't scale after some point, then you move to some other technology, and that technology stops scaling. You actually push its limits, but then you move to some other technology. But the fundamental issues always remain the same, in my opinion. Read disturb was there in any memory. It happens in hard disks also, actually. It's going to happen in any memory that we come up with, I believe. But we'll see. Okay, that's more philosophical, sorry. Okay, so you can read the flash memory works. There's a lot to do here. Okay, let me talk about two other solution directions, and then we're going to conclude this part of the lecture, which is the second topic. So I think there are two other solution directions for reliability and security problems, but based on what I said, this is really not a really long-term solution direction, but it could patch for a while. So replacing or more likely augmenting DRAM with a different technology, I think this is really interesting. Unfortunately, different technologies have different downsides also. They all have some sort of reliability problems. In fact, as we discussed yesterday, phase change memory, for example, has an endurance problem. You keep writing to a cell, after 10 to the 6 writes, 10 to the 7 writes, the cell dies. You cannot read or write from the cell. And that's true for flash also, for different reasons. So that problem exists, and that problem doesn't exist in DRAM. Right? So DRAM is actually still a not bad technology. But we need to enable these technologies because who knows, they can actually aid the scaling. Maybe you have very little amount of DRAM in the system, and you have a huge amount of non-volatile memory that is more scalable, perhaps, because it's resistive. You can reduce, you can have more capacity. You'll still need to solve the reliability issues, but that may not be a bad solution. Hybrid memories, as we discussed earlier. I think the second solution direction is very, very interesting also. You can embrace unreliability, right? You can design memories with different reliability and store data intelligently across them. I think this is really promising, actually. There's a lot more that needs to be done. The first and only paper that we wrote in this area was at DSN in 2014. I'll give you the idea in the next slide or so. But I think fundamental solutions require a little bit out-of-the-box thinking. You require co-design across the hierarchy. Essentially, both this solution and the DRAM solutions that we've been talking about require understanding of the devices and changing of the interfaces over here. And maybe you need to change your algorithms also at some point, especially with non-volatile memory and if you want to embrace unreliability over here. You really need understanding across the stack. And I think this is a really critical skill to develop. All of you guys are much younger and you have a lot more years ahead in front of you. If you actually understand how the entire stack works and how you can do the trade-offs across the different parts of the stack, you can build much better and much more secure systems. Replace that security with any interesting metric that you want to optimize. Higher performance, more efficient. If you understand this, you do much better. Let me give you one example, and this is just scratching the surface. So let's look at an application and different data in an application. This is true for different applications also. Let's look at the memory error vulnerability. You get a bit flip. How vulnerable is different data? Some data, basically nothing happens. If you actually flip a bit, like in a video, nobody notices, right? If you flip a bit in, I don't know, in some data part of the web search engine, nobody notices because everybody looks at the first page of the Google search results, right? If it happens in the 10th page, who cares? That's an example. But there's some other data that's extremely important. It's a pointer to your index, or it's your index to your database. You get an error, you get a completely different result. Or it's a pointer, you get an error, you completely crash the system, right? So that's clearly unacceptable. So clearly there's a distinction between the data. There's vulnerable data and there's tolerant data to errors. If you can identify this, and it's not an easy task, somebody needs to be able to do it because it's very semantically related, right? Can you do it automatically? I think it's very tough. Somebody needs to provide you information about the semantic value of data. But if you can classify it as vulnerable versus tolerant, maybe you can design a system that looks like this. You have some amount of reliable memory, maybe little. That's very high cost. And you have a lot of amount of low cost, unreliable or less reliable memory. And you can decide, you can think about how do you actually build these chips. There's a huge design space in terms of how you build these. For example, this could be a technology that's very fortified. It can have a lot of ECC. It can have a lot of row hammer protection. And maybe here you don't care about row hammer that much, right? Because you don't put security critical data over here, right? Okay, so we've done this sort of study with Microsoft. Basically, we looked at their web search workload. And if you look at the data center systems that everybody designs today, there's ECC, error correcting code DIMMs. And one of the questions that we wanted to answer at that point in time was, can we get rid of ECC from most of the system to have a much simpler and lower cost system, as well as a more scalable system? Because if you get rid of ECC, now you get rid of some power and you can add more servers potentially, right? It turns out if you're actually intelligent about partitioning data in your workload, maybe not extremely intelligent, but somewhat intelligent at the memory region level, you can get rid of ECC from most of the system because most of the data doesn't need as much error correction. As a result, you can reduce the server hardware cost by 4 to 5%. And you can still get a very good availability target, 99.9%, which means that you're not sacrificing that much reliability while reducing the cost. So this is one example trade-off that you can enable if you have this sort of heterogeneity inside the memory system. So what do you need to do? Of course, if you want to really generalize it, you have different applications and different data. You need to understand their characteristics and classify application memory error tolerance. How do you do that? I think there's a lot to be done in this area. Who does it? Are there intelligent methods that reduce the burden on the programmer to do this? Do you do it at the data structure level? Do you do it at the memory region level? I think there's benefits to data structure level information also. But clearly there's a spectrum, vulnerable data, tolerant data. And after you know your data very well, you can map that application data to this heterogeneous reliability memory system with hardware-software cooperation. I'm not going to talk about exactly how you do it because this really spans the entire stack, right? We're actually really talking about the algorithmic level almost over here. You need to really understand what your algorithms do to the data, right? Whereas here, we're at the very low level over here. How do you design this heterogeneous reliability memory to take advantage of what's happening at the very high level, right? This is an example over here, but there could be many, many design choices over here. That's why I think this is a huge area where you can enable very, very interesting solutions. And this is one example of the trade-off space that we just carved out. Again, I'm not going to go over this in a lot of detail, but this is crashes per service per month, memory cost savings, incorrect queries out of 1 million queries, single server availability, and server hardware cost savings, overall hardware cost savings. And ideally, you would like all of these to be optimized. Basically, the curve that covers more area is better in this case. Outer is better. And HRM is heterogeneous reliability memory system. Less tested is just less tested systems. Or less, if you have just less tested memory, that's not good, as you can see, right? It saves you costs, but it's terrible in terms of reliability and correctness. But if you have heterogeneous reliability memory and you're intelligent about how to allocate your data, you can get closer to over here. But a typical server system that's error correction code protected, it still crashes less, as you can see over here. Its correctness is still the highest. A little bit, but still the highest. So there's a really interesting space to explore over here, and you can actually have other dimensions over here, right? This doesn't include energy efficiency, for example. Okay, but you can read the paper. I think there's a lot to do in this area. Okay, basically, let me summarize this second topic. Basically, memory reliability is reducing, and reliability issues open up security vulnerabilities, and these could be very hard to defend against. Rowhammer is a very interesting example, I think. Its implications on system security research are tremendous and exciting, and there is always a new Rowhammer attack that's happening. I think I didn't even cover the last one. There was an attack on Rampage that's recently. That was very recent. You can take a look at it. If you search for it, you'll find it. But I think there's good news. There's a lot more to do for us as system designers, right? And I think if you understand the systems, if we architect well, and if we develop design and testing methods and security, put security as a first-class constraint from the very beginning of the design, then we can do much better. Okay, that boils down to basically designing fundamentally secure, reliable, and safe computing architectures. And there's a lot more over here. I think one key takeaway is we need intelligent controllers to be able to enable this. I don't think there's any other way, actually. Especially if you want the security as a first-class constraint, you cannot stay with a dumb controller that you cannot change in the field. I think those days should be gone. Should have been gone a long time ago, but should be gone from now on. Okay, there's a lot more in flash memory reliability and security, but I'm going to stop here for this part of the talk. Any questions? This is a really good time to ask questions. Yes?
When you showed the distribution of the variable retention time, that it's so large.
Yes.
Does it have any, is there any relationship between where physically on the chip that cell is? So for example, you showed, it can be a large difference, right? Is that testing one cell, or are the cells around it also?
That's it.
Also exhibit the same behavior, or is it?
Yeah, that's a really good question, actually. So it turns out variable retention time is relatively random. Based on our results, it's randomly distributed across the cells. There is no locality to it, as far as we know. But who knows what happens when you go down to 7 nanometers, right? I think we'll need to understand it better at lower nanometers, because it's really, in the end, it's about charge getting trapped, and we don't really have a good model for that. Nobody, as far as I know, has a good model at the circuit level about charge getting trapped into the access transistor. I call it the quantum-like effect. Maybe some quantum computing folks should look into it. But I'm not sure if they have a good model of quantum computing also at that level. Any other questions? Yes?
So overall, what are the most dominant types of errors for DRAMs? Like if you look at all flip flips and hard errors, and all that.
Yeah, that's a great question. I mean, it really depends on the system. So Rowhammer is not dominant in real applications. It happens in real applications, but it's not the dominant error. But it could, if you want to launch a security attack, you could make it the dominant error. So it really depends on the system. But if you look at a data center system, cell errors are actually, there are a lot of cell errors. Single bit errors that you see, or multi-bit errors that you see in the cells. There are a lot of channel errors also. And it depends on also how good you're with the system design. As I said, if you haven't seated your DRAM really well, then your channel errors become dominant at a given point in time. And also, we don't know what we don't know also, right? There's also this interesting thing. We may actually be getting uncorrectable errors that is affecting some part of the data that we're not reading, right? That's also happening. Sometimes we get, there was this really good talk at DSN in 2014 by a Google engineer. If you look it up, basically he talked about a bug that they chased for 8 months or so. This was crashing some important part of the software, and they eventually figured out that it was a bit flip in memory. So it's affecting basically the systems, and if it's going to increase, it's going to affect us more. So at some level, it doesn't matter what type of error it is. What else? Yes, I think we'll continue with questions because we don't have enough time to start the next topic. We'll start it tomorrow. Yes.
For Rowhammer issues, I don't know why don't the manufacturers discover this issue during their simulation? Like if one of the reasons is like electronic coupling, then I believe the manufacturers must have done some like electronic magnetic simulation. Then why don't they have discovered this issue?
Yeah, I think that's a really good question. Maybe you should ask some DRAM manufacturers. So I think, okay, there are two answers to this. One is, it's not easy, right? This actually requires, first of all, you could do circuit simulation, but this is actually really, really hard to simulate. And all of this electromagnetic coupling, I think we don't have very good models for that sort of simulation. So I think that is very difficult. But you could say, oh, why didn't they test memory using all of these hammering? Then that increased the test cost a lot, actually. If you think about how to really figure out whether a memory is vulnerable to roll hammer or not, you should do a lot of testing. And if you think about the mentality of the DRAM manufacturer, they're optimizing for cost. Anything that they add to increase that test cost goes directly to their profit margin. And as a result, you get what you get. I think one of the issues, you could also say they should have had predictive models, and I agree with that. I think that's something that's lacking in most of industry. We don't really have very good predictive models as to what might happen as we scale the circuits down to smaller nodes. And that was the first point that I have over here. We really need to understand and build predictive models. But your question is really excellent, actually. Why didn't they, based on all of the knowledge that they had in the past, why didn't they do it? I think it's because it's difficult. And it's going to be even more difficult, actually. This phenomenon, the roll hammer phenomenon, is going to increase in the future. And we really need architectural solutions. In my opinion, there's no other solution than architectural solutions, like what we've discussed, the probabilistic adjacent roll activation, unless someone comes up with a technology that's resistant to it. But that doesn't seem to be in sight anytime soon. Yes?
Can you please do the slide 65?
Slide 65? Yeah. Oh, you would like to? Okay.
Yes, there's a plot that I'd like to ask a question.
You found an error in the plot?
No, there is no error, right?
That's okay. I can online correct my slides. That's actually what I like doing. 65. This one? Oh, sorry. Yeah, this PowerPoint. As you can see, PowerPoint is very smart. It's 20 out of 36. Yeah, 65. Oh, okay, that's earlier. Adjacency, aggressor, and victim. That's earlier. That's in roll hammer, right?
Yeah.
Yes, this one. Okay.
Yeah. So, do you expect any change in this graph based on the size of memory?
Based on what? I'm sorry.
Size of memory.
No, I don't expect the distance between aggressor and victim will change based on size of memory. I think because this is really. Okay, maybe you have a point. It might change. It depends on what these are. I think if these things that are far away are because of remapped rows, which I believe, it might change with the size of memory, size of the chip, because as you increase the size of the chip, you're probably at a much lower technology node, which means that you probably have more errors that you've discovered, and your remappings may actually increase. So that might be one reason this might change, but I don't expect it to change really, really heavily, because unless the manufacturers increase the number of rows that are used for remapping internally. There might be a case for that, actually. If you have these, so actually people have been proposing, oh, why don't you actually have more rows inside DRAM that are not used for anything, and whenever you discover errors in some other rows, remap the rows that you were using to these other spare rows. If you have systems like that, then you have a lot more spare rows, and this figure might change. Yes. Yes.
So you mentioned about the need for intelligent controllers.
Yeah.
But the controller usually sits outside the DRAM bit, right? So if a whole DRAM package fails, so the server operator needs to replace that. And in that case, like the online profiling of the DRAM is to be done again by the controller or things like that.
That's right. If you replace the DRAM, you need to have new profile.
Instead of having intelligent controllers, there's a need to have intelligent DRAM.
Yeah, we'll talk about that tomorrow. So intelligent controllers, this doesn't mean that controller has to sit outside DRAM. It could be in a 3D stacked memory chip, for example, where there's a logic layer underneath the memory layers, and controller can be over there. So controllers, I agree with you, but I think we need intelligent controllers regardless. Even if the controller sits outside, Rowhammer can be solved with existing controllers, existing systems, without changing DRAM at all, if you have an intelligent controller, basically. But I think there are trade-offs between having the controller in the DRAM or in the logic layer underneath the DRAM or on the processor chip. But this is going to be a hot research area going forward. Like in the past, for example, memory controllers were actually not on the processor chip, right? If you go back, I guess 15 years, AMD was the first general purpose system that put the memory controllers on chip, and Intel followed suit quickly because it was a really good idea to put the memory controller on chip. But before that, you had these memory controller chips that were manufactured separately. The processor used to access that memory controller chip, and memory controller chip used to access memory. Now, because of integration, we're able to put many things on the same chip. But where does the memory controller go is now a good question, right? Should it be a separate chip? That's a lot of communication overhead. Should it be on the processor? Now it doesn't know enough about DRAM. There needs to be a protocol, but it can discover a lot. Should it be on DRAM? There are also benefits to this also. Now it doesn't have enough information from the processor, right? I think going forward, there are really, really interesting technologies where you 3D stack everything. I think that this is maybe a lot more into the future, but for example, there's this next project at Stanford that's looking at stacking everything on top of each other. You have non-volatile memory technologies, and you have very small interconnects, vias, and you can have processors also. So you can have processing layers, memory layers, interconnect layers, and you can stack, mix and match many of them. If you do that, then there's no distinction anymore, right? Except for the length of your interconnect. Your interconnect becomes a bottleneck again. But I think your question is very good. It opens up a lot of other questions. But we'll talk about controllers close to DRAM tomorrow. Yes, in the back.
So are there some research, like people take advantage of the randomness of physical bit flipping and take advantage of that by introducing more randomness in their algorithm?
I see. That's a good question, not that I know of. I don't know of such research, even if it exists. It could be interesting, though. So people have, we have been looking at, and other people have also been looking at approximate memory. So if you actually, and I'll talk about that tomorrow a little bit, well, maybe the next day. If you reduce the latencies, you get less reliable memory. And as a result, you get some randomness. And you can use that to build a physical unclonable function, for example, or a random number generator that you could use in your algorithms. So this is similar in mindset, I think, as what you're talking about. So we've done some of that. But I don't know of any work that takes advantage of the randomness in their algorithms, for example.
Yes, for example, there are some deep neural network algorithms.
Yeah.
When they do quantization, they tend to quantize high precision values and low precision values with some randomness.
Yeah.
So in that case, if we can take advantage of and we can also save some power by...
Yeah, that's true. I think by making your memory more approximate, by playing with some of the levers, you can actually accelerate machine learning. I agree with that completely. We'll talk about that. But not necessarily machine learning context. A lot of applications can benefit from that sort of trade-off in approximate memory. But I think there's more to do to show that that's really how it works. What else? Maybe okay.
So kind of related to the memory controller question, the FTL and flash memory, that the storage vendors, they have bare leveling, garbage collection and all that. Have you looked in the flash memory context if that is not sufficient? What are the kind of issues? Like for example, for MLCs, for 3-bit MLC and even more, does that exacerbate the problem? Does it make it worse?
Yeah, certainly. As you increase the capacity in flash memory, ignore 3D NAND, for example, but what flash memory vendors do to increase the capacity is you have a voltage range in which you store the value. You can store only 1 bit by chopping it into 2 ranges, right? 0 or 1. You could store 2 bits by chopping it into 4 ranges. You could store 3 bits by chopping it into 8 ranges. And as you chop it into smaller ranges, the error rates increase certainly. And as a result, your endurance also reduces significantly. So certainly your memory becomes less reliable as you go into MLC, TLC, and QLC actually, if you want to store 4 bits per cell. There's no question about that. And that's very fundamental.
But
that's true for other memories also, like STT RAM, phase change memory, yes.
But doesn't FTL kind of...
Yes, FTL tries to minimize those errors. You add error correction, you add signal processing, and that's what that paper is about, the error characterization paper. If you're really interested in that, you should read that long survey paper. That's the result of 8 years of research. But it doesn't fundamentally change the fact that you get more errors. It corrects as much as possible, but you get fundamentally much lower endurance to begin with triple level cell, for example. Okay, I think this is really a good time to stop. Thanks for asking all the questions. Tomorrow we'll cover in-memory computation. It's going to be very different from today. It's going to be we're going to switch between applications as well as circuits, and we're going to keep doing that. Very similar to what we covered at the very end. Okay, see you tomorrow.